We start with unit number 3 for basic tools. I want to share it. The screen. Okay, here. Starting, we go back to the first key. Unit 3 deals with energy, the types of energy that is there, and I will introduce the law of conservation of energy so that you can recognize and apply this particular law towards a self-study problem at the end. After that, we are going to do measurements and what are the units that are there. The first system international unit, fundamental units, metric units, and temperature scale. And when we come to the temperature scales, we will end this particular unit, and then students are expected to complete their self-review study so that they can ensure that they have understood the concept. First thing, the basic principles. Energy is the capacity to do work, and it can be classified as kinetic or potential energy. Kinetic energy is associated with motion. Therefore, you can have motions at the particulate level, which basically is at the thermal energy, where you cannot see it, but the molecules are so small that we cannot see it, but we can feel it. And also energy is associated with macroscopic objects, such as when we throw a ball or falling water. Then other kinds of kinetic energy is the movement of electrons in a conductor, electrical energy, wave motion, which is a transverse motion, and compression, which is acoustic or sound energy. Matter, because it consists of atoms and molecules, is in continuous motion. The second form of energy is potential energy. It is a result of the storage of energy because of an object's position. First type is gravitational energy. If you hold an object high, then it possesses energy. Waterfalls is another type of stored energy. Stored energy in a water tank on a hilltop. The next is energy stored in an extended spring. Another kind of energy is the energy stored in molecules. For example, chemical energy when it is produced from a battery, or energy produced by food, or when food is produced and stored by photosynthesis. You have the food sugar that is produced during photosynthesis, and that can provide energy. Energy associated with charged or partially charged particles, electrostatic energy, and nuclear energy, a result of fission or fusion. Now, before I go any further, I want to introduce the law of conservation of matter. Even though I've not written it over here, I want to let you know that the law of conservation of energy states that energy can neither be created nor destroyed, but it can be transferred from one form to the other. We know that this statement is true is because when you're driving a car and suddenly put a brake, you know that the tires get hot because of friction of the tire with the road. And so this energy that is lost when we drive, the wheels get hot. When we stop, the wheels get hot. And so we find that the energy of motion can be measured in terms of the heat energy. And so we need to know how to measure the heat energy, and we'll come to that very, very shortly. Before that, we have to know how we are going to measure. Any type of observation requires measurements. So in other words, whenever we do observation and data collection, we need measurements. And there are two parts to measure all measurements. A number, that is quantitative piece, a unit that is a qualitative piece, which defines what you are measuring and how you are measuring. A number by itself is somewhat meaningless without its units. Consider this for one's wages. If I say that you have $100 and don't tell you how you're going to give the $100 or get the $100, then it makes no sense. And further, if I tell you the $100 is per week, I'm sure you're not going to peg it up. Whereas if I tell you that, hey, I'm going to pay you $100 per hour, oh, I'm going to take that job, definitely. Because you know that if you work 40 hours, you're getting $4,000. That's not a bad deal at all. And therefore, you can see the significance of units that are there. Now, when we do measurements, we have to follow certain rules. And one of the rules that is set by the System International for Units. This is the body that decides the appropriate unit terminology that is used. And every use has a different base unit for each quantity. Now, when we say a base unit, basically, it means that that particular unit, when we write it, the quantitative number will be 1, followed by the qualitative aspect of what you are measuring. Mass is in kilograms, and the abbreviation is kg, but there is a slight difference here, and I will explain to you in the next slide. Because the base unit for mass should be 1 gram and not kilogram, but that's how it is represented nowadays. Length, the name of the unit is meter, and it is M. Time is expressed in seconds, temperature in Kelvin, amount of substance in mole, electric current is in ampere, and luminous intensity is candela, and it is expressed as CD. The electric current abbreviation for ampere is A. Now, if you note, there are 7 units over here described on this chart. Now, before we go to the fundamental units, I want to do the metric system prefixes. Prefixes convert the base units into units that are appropriate for the item being measured. Now, this chart one needs to know in order to do conversion towards the end when we come for quantitative calculations in the next unit. So the prefix gigas is given an abbreviation capital G. Its value is 10 raised to 9. Mega is capital M. Its value is 10 raised to 6. Kilo is K. Its value is 10 raised to 3. Deci is D, 10 raised to minus 1, which we can write as 0.1 of a meter. Centi is 10 raised to minus 2, and so it is 0.01. Milli is 10 raised to minus 3. The symbol is lowercase m. Micro is a special unit because its abbreviation is mu, the Greek letter mu, and it equals 10 raised to minus 6. Nano, lowercase n, 10 raised to minus 9. Pico, P, 10 raised to minus 12. Femto, F, 10 raised to minus 15. So these are the units that are generally used when we are working with or solving problems in chemistry. Now, at the introduction of SI units, we saw that there were 7 units necessary to describe the universe. However, for everyday purposes, you just need 4 fundamental units, and they are mass, length, temperature, and time. Now, how do we determine these 4 fundamental units that is required? Mass is measured using a balance. The balance is calibrated to a standard mass kept in London or Paris. Length is measured by using a ruler. The distance is calibrated using the distance between 2 points on a rod, calibrated using the sodium D lines. The sodium D lines are very close to one another. On excitation of a sodium atom, you will see that you will get a yellow color which is so close to each other that we cannot differentiate it. But if we pass it through a prism, then we can see the two different lines. And these lines are differ by a very small nanometer, and therefore we can use that as the standard. The time is measured by setting the clock using the atomic clock, which is set always on the New Year's Day. One other unit that one needs to know is the unit of capacity, which is called as the volume. Most commonly used metric unit for volume are the liter and the milliliter. A liter is a cube of 1 decimeter long on each side. So the volume of 1 decimeter cube is 0.01 raised to the power 3. That is equal to, if you say that 1 decimeter is equal to 10 centimeters, then 1 decimeter cube is equal to 1 liter is equal to 10 times 10 times 10 centimeter cube, which is equal to 1,000 centimeter cube. Now, a milliliter is a cube of 1 centimeter long on each side, and 1 centimeter cube is equal to 1 milliliter. And this is the spot where we convert the unit of length, centimeter cube, to the unit of capacity, 1 milliliter. And that is a very useful unit when we are doing different types of experiments. Next, we are going to temperature. We know that all forms of energy can be converted into heat. And therefore, we need to know how we can find or determine the changes in the heat content of any substance that is there. In order to measure the heat content, we use an equipment called as a thermometer. What is a thermometer? It is basically a glass bulb containing a liquid, which on heating rises up and on cooling falls down. And the bulb contains this particular liquid. The characteristic of the liquid or the property of the liquid is that it must heat up very quickly and also must lose heat very quickly so that you can measure temperature of other units, other materials that are there for your experiment. The material that is used to calibrate the thermometer is water. And the temperature that are used to calibrate any thermometer is water. And the temperature when water freezes and when water boils. Water freezes at 0 degrees Celsius and boils at 100 degrees Celsius. The difference is 100-degree intervals. On the other hand, when you use the Fahrenheit scale, the water freezes at 32 degrees Fahrenheit and boils at 212 degrees Fahrenheit. The difference is 180-degree intervals. So we can straight away look at it and say that 100-degree interval on the Celsius scale is equal to 180 degrees interval on the Fahrenheit scale, because both are measuring the temperature boiling point and freezing point of the same material. And from this we get one of the simplest and quickest relationship, that 1 degree Celsius is approximately equal to 2 degree Fahrenheit or 1.8 degree interval 1.8 degree interval on the Fahrenheit scale. Now we have the third scale, which we designated on the fundamental SI system, and that's the Kelvin scale. The difference on the Kelvin scale is the same as the difference on the Celsius scale, but the freezing point water starts at 273 degrees K, and the boiling point of water is 373 K. Remember that on the Kelvin scale, there is no degree written. It is just a symbol, letter K. Now we can convert from one unit to the other. From one unit to the other by using the conversion unit. And what is that? We find that if you want to go from Fahrenheit, if you want to go from Celsius to Fahrenheit, then all you have to do is multiply 9 by 5 times the degree in Celsius and then add 32. However, instead of remembering 9 by 5, if you divide 9 by 5, you get 1.8. So if you want to convert from degree C to degree F, all you have to do is multiply the degree C Celsius value by 1.8 and add 32. On the other hand, if you want to come from Fahrenheit to Celsius, then first we have to subtract from the degree Fahrenheit 32 and then divide that number by 1.8 or multiply it by 5.5 by 9. Either way, you will get the same answer. So here is a brief summary of the conversion from one unit to the other and for different temperature scales. First one, Celsius to Kelvin, all you do is add 273.15. Even though we added at the beginning 273, but 273.15 is much more accurate. And Kelvin to Celsius, just subtract from Kelvin minus 273.15. To go from Celsius to Fahrenheit, you multiply the degree Celsius by 1.8 and add 32. To come from Fahrenheit to Celsius, first you subtract from F32 and divide by 1.8. Kelvin to Fahrenheit, you cannot go directly. So you have to take a step by step. First from Kelvin, convert it to Celsius. And then convert the Celsius to Fahrenheit. So how do we convert from Kelvin to Celsius? You subtract 273. Then whatever the answer you get, you multiply it by 1.8 and add 32. And the reverse is the same. First, you convert Fahrenheit to Celsius and then add 273 to get the Kelvin scale. Now, here are a couple of problems that you can try and solve. I've given the answers, so you can do a quick review, study review for that. Same thing for conversion from Celsius to Fahrenheit and vice versa. And I think the next chart must be a conversion from Kelvin to Fahrenheit, so that all the steps that was put in the summary, you are able to use and understand the principle. And after that, we come to the self-study concept that is there. And here, this is where you will use your energy concept and the law of conservation of energy to find out and explain what has happened in going from the initial to the final value. And this is 2 balls are held in place, and then you can see the changes that take place. All remaining questions are based for self-study, and there are not many. At the end of this, I'm going to stop now. And at the end of it, we are going back to do some qualitative problems under measurements.